Matter is anything that takes up space and has volume. They don't ask you that on the regents, so I'm not even going to write the definition down. And your teacher might ask you the difference between mass and weight. And again, I'm just going to mention it verbally because they don't ask this on the regents either, but mass is the amount of matter something has, what it's made up of, where weight is just the pull of gravity on the object. But the main thing you have to know about matter is you have to know the difference between physical and chemical properties. And physical and chemical changes. And a physical property, we're going to talk about the phases of matter. So I think pH. And this, as far as you're concerned, there's 3 phases of matter: a solid, a liquid, and a gas. So if I think about water, which is made up of, you know what, I got to start all over. I'm starting all over. Okay, matter and energy. I am going to talk about the difference between an element versus a compound. So an element is the simplest form of matter, and matter is anything that takes up space and has some volume, which is length times width times height. But it's the simplest form. And if we go to the reference table right here, oops, wrong one already. Okay, if we go to the reference table, all of these symbols here are the elements. And if you notice, they are capital letters. So B represents boron, C represents carbon. And then if you notice, there's another element that has a C. So the second letter is always lowercase. So Ca is calcium and Cl is chlorine. So to represent an element, it's one capital letter, but if that capital letter already exists, the second letter next to it is lowercase. So the simplest form of matter is an element, and because it's the simplest form, it cannot be broken down by chemical means. Chemical means are changing into something new. That's different than physical change. A physical change would be whether it's a solid, liquid, or gas, like the phase it's in. That doesn't change the properties, but chemical change is when you turn into something new. But let me go into, again, if you see one capital letter, we know it's an element. If we see a capital letter with a lowercase, that's an element. And also you might see a capital letter with the subscript 2. That's the twins. There's 7 of them that are twins. They're called diatomic. These 2 here that I showed you are monoatomic. Mono means 1, so that's just 1 atom. So maybe we'd represent the C with a black dot. Maybe the Cu would be 1 white dot, and then H2 would be represented by dot diagrams, just 2 of the same stuck together. But anyway, those are all elements. But they're pure. Elements are pure. They cannot be broken down by chemical means. Now, if we talk about a compound is made up of 2 or more different, that's the key word, different elements. And I say C for compound is C for chemically combined. So if we have capital C with capital O, that's a compound because this represents carbon, that represents oxygen, and that's carbon monoxide. Where if you had a C with a lowercase o, that is cobalt, which is an element not a compound. This one's a compound because you see two capital letters. It doesn't just have to be two capital letters. Uh, it could, and that's a 1-to-1 ratio. There's, you don't have to put the 1 in, but H2O is water. That's a compound. And there's two capital letters, but there's two H's and one O. And that's very important. In order to have water, there's always two H's and one O. Two H's and one O. So that's a fixed ratio or fixed proportion. And again, those are keywords that they ask on the New York State Regents. So compounds two or more. And why do I say different elements? Because I could give you a diatomic element again, like O2. Those are two of the same. Therefore, that one's also an element. Here, it's not, and I'm going to abbreviate compounds, not a compound. So elements and compounds are both pure. And now we're going to talk about physical versus chemical properties. Well, let's think about some physical properties. Physical properties would be maybe the phase that it's in. And as far as we're concerned, there's 3 phases of matter. Even though there's a 4th phase, there's plasma, but they don't mention that on the Regents. I'm just strictly going by the Regents curriculum. The 3 phases of matter that you're responsible is a solid, liquid, and gas. So water could exist. Let's just use water as an example. Water could be an ice cube, and you'll see a little subscript S. Water could be in the liquid form that you drink, and water could be a vapor, which is a gas. It's still water, so that's why it's physical means here when you go from a physical change, like if you go from solid to liquid, that's a physical change. It's not chemical. Chemicals when you change it to something new, maybe taking hydrogen and taking oxygen and putting it together chemically to make water, that one is a chemical change. But this one is a physical property, the 3 phases of matter. And now I have to go into the definitions. What is a solid? A solid has the keywords they've been asking recently is crystalline, and it's a regular geometric pattern, and it, believe it or not, vibrates in a fixed position, but I don't see them ask that anymore. The only thing I see is regular geometric pattern and crystalline. And if they say which is crystalline, you have to know to pick a solid. And you're going to learn on the periodic table, if we want to mention it now, that most of the elements are solids. In fact, you're going to learn that right here. Let me put this in. Mercury right here is a liquid. Bromine's a liquid at room temperature. Iodine's a solid. This last column is known as noble gases, so you're going to have to know that these are all gases. And then there's 5 diatomic gases. These are the guys that exist as 2 together. There's one over here. It makes a 7 in the chart. But I say 5 gases because one's a liquid and one's a solid. But if I want to put a little subscript 2 over here, you have to know which are diatomic, and you have to know the phases. So, but that will come up when you do the periodic table. Okay. Now, we're going to talk about a liquid. A liquid if you think about it, if we have a glass of water, maybe we're going to fill it this high, maybe we're going to fill it this high. So it has a definite volume, right? We could measure out a certain amount, but no definite shape. Why no definite shape? Because you could have a fat glass like this and a tall glass like this, and you could trick a small child. You could actually put more in the fatter glass than the tall, skinny glass, and they'll pick the one that has more. But anyway, no definite shape. It takes the shape of the container. Let's talk about a gas. I've mostly seen the mask solid, on rare occasion gas, never really the liquid, but a gas completely, that's the key word, completely, or the other key word is uniformly takes the shape of the container. And we could just think of balloons, all the different shapes of balloons that you have. And again, a gas completely takes the shape of the container. So that's it. You look for little subscript G. So they might ask you, you know, which is solid, which is a gas, or they'll ask you to draw a diagram of it. A solid, I draw them together in a closed pattern. A liquid, I'd have like some of them touch. And then a gas, I have it all spread out. And if it's a diatomic gas, there's always like twins, there's always two of them together. So you have to draw a diatomic gas like that. Now I'm going to talk about more physical properties. Physical properties would be maybe whether it conducts electricity. If we have a metal, metals conduct electricity, and we're not changing anything, we're just making a statement that a metal conducts electricity. So that's a physical property. We're not changing it into anything new. And whether it dissolves in water, you know, if I say a salt dissolves in water, I'm not changing anything. That's a physical property. Density, we're going to learn later, is mass over volume. And that's just physical property. The temperature at which it boils, the boiling point, the temperature at which it melts, the melting point. That's just a specific value on the thermometer. These are all physical properties. Now, how would I know chemical? Chemicals when you change into something new. So you could think of rust. Oxidation is, you're going to learn this word later on, but it actually means something rusting. It's changing into something new. It's a chemical reaction. Another key word would be corrosion. Burn. If you burn paper, you're not getting it back. Form a compound. And then bubbling. Bubbling means maybe a gas formed and escaped. So these are all keywords you want to look for a chemical change. And on the regents, very important, you know the difference between if the question's asking physical versus chemical change. Now I'm going to talk about if you have a substance and it starts off as a solid and then you heat it up and then it starts to break down to solid to liquid, then it's completely in the liquid form, and then goes from liquid to gas, and then it goes completely into the gas form. That's known as the heating curve, and this is a physical change, not chemical, because again, we're just changing phase. And what I want to tell you is usually they graph temperature versus time. And solid to liquid has a special name. We know it's already melting, or we could say heat of fusion. That's, or melt. And if they want the melting point, you have to go over here and look up the degrees Celsius or whatever unit they're going to measure the temperature in. And liquid to gas is called vaporization or boiling. So if they want the boiling point, you have to look over here and see what temperature in degrees Celsius it is. And anyway, during this heating curve, I always say during a diagonal, you're adding heat. So potential energy, that's stored energy, it has the potential to do something. Potential energy is going to go up because you're adding heat, and then the thermometer is moving. So the temperature is moving here. That's why this is temperature, so you see the numbers are going up. But during the plateau part, which is right here, this flat line, very important, during a flat line, you're still adding heat. You're not removing it because you're still melting it. So potential energy, which now I'm going to call PE, to save time, goes up, but the thermometer just stops, it's increasing. At one point, it just stops. So the temperature is constant. And there's temperature by definition is average kinetic energy. So that's the first thing you have to know. Temperature is a measure of average kinetic energy. It's not a form of energy, it's a measure of energy. And now I'm going to talk about the forms of energy that you're responsible for on the regions. I say mech, T. Okay, this is not all the types of energy. This is the energy they ask on the regions. They ask mechanical energy. Then they'll say either electrical or I'll say electromagnetic. Then there's chemical energy. And then there's thermal energy. So I just say mech-T. And by the way, thermal, I take that RM. And what does thermal energy means? It means random motion, right in the word. And they ask this a lot. And this particular chapter just has a lot of definitions, unfortunately. It's just the basics of chemistry, and you just have to go through it. So we're going to talk about I'm going to go back now and talk about the cooling curve, and then I'm going to talk about all the phase changes that could be. Cooling curve, you might be starting with a gas. You have to read the question because maybe it's just a piece of the graph where you're starting over here as a liquid. So if you label it a gas at the diagonal, you're not going to get the credit if it says starting as a liquid. So always read the little question in front. But anyway, here it's a cooling curve. So during a diagonal, because we're always graphing temperature versus time, the temperature is going down here because we're removing heat, and potential energy is also going down. But during a plateau, we're still removing heat, we're still removing PE, but the thermometer is constant because it's not moving. And by the way, this part here is called the freezing point. And if you notice on that other curve, this was liquid to solid, so the freezing point is the same as the melting point. And on a thermometer, there's two fixed points. You have the melting point and the boiling point. And the only one you really have to memorize is water. Water melts at 0 degrees Celsius, and 273 Kelvin is the melting point. Sorry, this is confusing the way I wrote it. Let me do that. And then these two are this. All right, let me redo this. Okay. There's two fixed points on a thermometer. There's the melting point and the boiling point. The boiling point is 100 degrees Celsius for water, and the melting point is 0 degrees Celsius for water. They might ask you it in Kelvin, which is 273 K, and then the boiling point is 373 K. If you notice, they're both based on a scale of 100. So since they're both based on the same scale, if Celsius goes up by 20 degrees, Kelvin will also go up by 20 degrees. Now, well, they don't use degrees in Kelvin, but Kelvin will also go up by 20. And these fixed points on a thermometer for water, you have to know if they ask you the melting point or boiling point of a different element. There's table S, which I'm going to try to pull out to show you. I don't even know where my table S is. I'm not going to show table S. Table S on the periodic table lists all different elements and their melting point and boiling point. So if on the regions they ask you what's the melting point of like sulfur, you're not going to have it memorized. You're just going to go look it up. Now, another thing they mention in this chapter is the law of the conservation of energy. And that's just saying that law of the conservation of energy. And that's just saying that um, matter is neither created or destroyed. And I just say mech, mass, energy, and charge is conserved. So if they say what's conserved, mass, energy, and charge. And mass means you have equal weights on each side, and charge is equal charge on each side, and energy. I'm not going to talk about energy. I'll have to cut that out. Now, if we talk about some phase changes, we already said heat of fusion. I think there's an S in the word, so it's going from solid to liquid. Then there's sublimation. And again, I see an S in the word. And I say skip the liquid. It's when you go from solid directly into gas. You skip the liquid phase, and that would be like iodine solid or dry ice, which is carbon dioxide solid. It goes directly from solid phase right into the smoke. And then we have vaporization. How do you form vapors? Liquid to gas. And then we have deposition. See the word deposit there? It's gas to solid. Then we have solidification. That's forming a solid, so that could be, that's liquid to solid. Condensation. And that's gas to liquid. And you just have to know all these definitions. And that's basically it. And I guess I could just go over, let me think about it. Yeah, that's it. That's it for this chapter. I'm basically gonna do some problems with these definitions on another video. I want to show you how to balance some equations. So first I'm going to talk about how do you get the number of atoms. To get the number of atoms, it's the coefficient, which is the front number, times the bottom number, which is called the subscript. So it's coefficient times the subscript. For instance, if we have H2, the number in front is a 1 and the subscript is a 2. So you say 1 times 2, so there's 2 H atoms. So now let's just say I have CaCl2. Again, I'm going to put a 1 in front and a 1 over here just so I know. So we have 1 times 1 because it's front times bottom. So we have 1 Ca atom. And then we have 1 times 2. So we have 1 times 2, front times bottom, so 2 Cl atoms. I'm going to do another one, SO2. I'm going to put a 1 here and 1 here. So we have 1 times 1, or a 1 sulfur atom, and 1 times the 2, because it's front times bottom, or 2 oxygen atoms. Now, what if we have a parenthesis? I'm going to again put the coefficient in front. So I have 1 times 3, or 3 Ca atoms. And I'm going to distribute here and distribute here like it's in math. So I actually have 2 P's and 8 oxygens, but then I got to remember that 1 in front, but 1 times the number won't change it. So I have 2 phosphorus atoms and 8 oxygen atoms. And this is very important in order to do the balancing of an equation. Okay, now here, there's an imaginary 1 here. So if I do front times bottom, I have 2 CAs. 2 times 2 is 4 oxygens. and 2 times 2 is 4 hydrogens. And the reason why I like to do that is because in order to balance an equation, we want equal atoms on each side. So I'm going to start with N2 plus H2 yields NH3. So I'm going to start with N. There's 2 times 1 here, so we have 2 N's on that side. And I have 1 N here. So I have to put a 2, and I can't just shove a 2 down there because this is a compound. It's 2 elements in a fixed ratio. You can't just change the subscript. You have to change the number in front, which is known as the moles. So if I put a 2 in front here, now I have 2 times 1, so I have 2 N's and 2 N's. But now I have to look at my H's. I have 2 H's here, and we have 2 times 3, which is 6 atoms of H's. So I could just put a 3 in front here. So now I have 2 N's on the left, 2 N's on the right, 6 H's on the left, 6 H's on the right, and now I am officially balanced. I'm going to try another one. And by the way, you have 2 things, 2 going to 1, and that's called synthesis. We might as well practice that now too. You have to know these chemical reactions with what they're called. So here we have 1 compound breaking up into 2 substances. So 1 breaking up into 2 is the opposite of synthesis. That's called decomposition. Don't get decomposition confused with deposition, which is gas to solid. Okay, but back to this. We have 1K, 1K. So far, so good. 1Cl, 1Cl. So far, so good. But then we have 3 oxygens and 2 oxygens. So I think of math that you need a common denominator. That between 2 and 3, the common multiple is a 6. So if I put a 2 in front, now I have 6 oxygens. So if I put a 3 in front here, 3 times 2, because you multiply front times subscript, now I have 6 oxygens. So now I just have to balance. We have 2K and we have 1K here. I'm going to put a 2. 2Cl, 2Cl, and now I'm totally balanced. Now next one, I have NaCl, that's a compound, plus a diatomic element. And now I have a different compound and a different element, and that's called single replacement. Single replacement's when this element is stronger and it takes the metal away and displaces the non-metal there. But let's just try to balance this. We have 1 Na here and 1 Na there. Looks good. 1 Cl. You have 1 Cl here and you have 2 Cl's here, so you got to put a 2 in front to balance it. So now we have 2 Nas, 2 Cl's. 2 Cl's, but 1 Na, so you have to put a 2 there. But now the F's are balanced. We have 2 F's here, 2 F's here, and we're balanced. Sometimes we put a 1 in front, but you don't have to. The next one, we have 2 substances going to 1, so that's called synthesis. And again, I have 2 H's here and 2 H's here. That looks good. I have 2 oxygens here, but I only have 1 here. So I have to multiply this one by 2 times 1 to give me the 2. But now my H's were affected. Now I have 4 H's. So all I have to do is put a 2 in front, and now I'm balanced. And again, you don't have to put the 1 there. I mean, if they asked what's the sum of the coefficients, you would say 2 plus 1 plus 2. But they ask that on the old regents. They don't ask the sum of the coefficients anymore. So here's another one. I have a compound plus another compound. And then you see the Ag took the nonmetal from the one compound, and the Mg, oops, I drew that sloppy. We can't see what that is. Okay. So here we have Ags with the NO3, and now Mgs with the NO3. And here Mgs with the Cl, and here Ags with the Cl. So that's called double replacement. And with double replacement, I see two compounds on each side. And they switch partners, if you want to say. So let's just look. We have Ag on the left, we have 1. Ag on the right, we have 1. So far, so good. 1N here, but here you got to multiply. We have 2N, so I'm going to put a 2 in front. Now my Ag changed to a 2, so I'm going to put a 2 here. So now I'm going to check. I have 2 Ags, 2 Ns, and 6 oxygens because you multiply. And I have 1 Mg and 2 Cls. Now I'm going to check the other side. 2 Ags, so far so good. 2 Cl, so far so good. 1 Mg, so far so good. 2 Ns and 6 Os, and I'm totally balanced. Next one. Okay, for the next one, I have 1 Al and we have 2 Al, so I'm going to put a 2 in front. Now I have 6 Brs, and I only have 1 Br, so I have to put a 6 in front. 2 Ks, I have 6 Ks, so I have to put a 3 in front to make 3 times 2 is 6. 3 S's, 3 S's, 12 O's, 12 O's. Looks like I'm balanced. And again, this is double replacement chemical reaction because I see all compounds. Okay, next one, CH4. Carbon plus oxygen gives you CO2 plus water. That is called combustion, and that's how I remember that. Carbon plus oxygen. These are harder to balance. I have 1 carbon and 1 carbon. So far, so good. Now I have 4 H's and 2 H's. So I'm going to put a 2 there. Now I have 4 H's. Here I have 2 oxygens, and here I have 2 plus 2 over there. So I have a total of 4 on the right. So I have to put a 2 here, and then I'm balanced. Here's another combustion problem where I have 8 carbons, so I'm going to put 8. I have 18 hydrogens, so 9 times 2 is 18. Now I have 8 times 2, which is 16, plus 9, which is an odd number of oxygens. So it didn't work, because I'm not, well, I can multiply. I could get rid of it with an odd number, but I'm not going to go into that. So basically this didn't work. So when that happens, I'll show you what we'll do. We'll just cross it out. And it did not work with a coefficient of 1 in front. So I'm going to change this to a 2. Don't just jump around. Now do 2. So that's 2 times 8, which is 16 carbons. So I'm going to change this to a 16. And then that's 18 times 2, which is 36 H's. So I have to put an 18 here. But now if you notice, we have 16 times 2 oxygens, which is 32. And you have 18 there. And then if you add that up, we actually have 50 oxygens here. So then that's easy. You could just put a 25 here. And if the 2 didn't work, then you try a 3 and just go in consecutive order. Here's another one. P plus O2 gives you P2O5. And again, this is two substances going to one, so that's called synthesis. So we have one P here and we have two here, so I'm going to change this to a 2. And now we have 2 oxygens and 5, so you have to think of a common multiple or a common denominator. So I'm going to put, even though we're not doing math, but, we're not doing fractions, but I know 10 would be the number, so I'm going to put a 2 here so I get 10 oxygens. So then I have to put 5 here to get 10, but we changed our P. P changed to 4. No biggie, just cross it out and put a 4, and we're done. Here's another one. S8 plus O2 yields SO3. Well, we have 8 S's, so I'm going to put an 8. Now, 8 times 3 is 24 oxygens. So that's easy. Just got to put 12 here because 12 times 2 is 24. And now I'm balanced. And that's 2 going to 1, so that's called synthesis because we have here 1, 2 things going on this side to 1. That's called synthesis.